Hello everyone, I'm Hamza and I'll continue with my review on Helm research paper, which is Holistic Evaluation of Language Models. And today, what we're going to be talking about are the experiments and results, the related work and discussion, what is missing, limitations and future work, and the conclusions. In my earlier videos, I talked about certain few things like the metrics, the targeted evaluations, and if you haven't yet watched them, you should go and watch them. So the experiments and results, we'll talk about the meta-analysis, the prompting analysis, the task-specific results for core analysis, the targeted evaluations, and the human evaluations. So the meta-analysis is how we evaluated 30 language models, including Da Vinci and Loom, across 16 scenarios. Later on, I'm going to show you a picture showing all the 30 language models we evaluated. And this evaluation covered seven metrics, such as accuracy, fairness, bias, toxicity, and the three others. The goal was to answer key questions in the field, such as whether model accuracy correlates with scale and if more robust models are less biased. So we started with the intermetric relationships. So in the relationships, we saw accuracy, robustness, and fairness being strongly correlated as they correlate with each other. And this suggests that models are accurate tend to be robust and fair, though this contradicts some previous studies that were done before. So the generative harms, the toxicity generally shows that like correlation in other metrics, it shows very little correlation, except in specific scenarios like narrative QA, which we particularly use to show toxicity. Then bias has a complex relationship with accuracy and fairness, indicating trade-offs between reducing bias and improving fairness. As you reduce bias, you improve the fairness of the model, of the metric. Then the relationships between metrics are complex and often scenario dependent. What they mean by this is with different models, we have different relationships with the metrics as they don't coincide with all particular models. And efforts to improve one metric, reducing bias may negatively impact another. As you reduce bias, you can increase toxicity. So as you can see here, this is a relationship between a particular metric and accuracy. So as I said before, we saw that accuracy and fairness are strongly correlated, as you can see right here. This is the fairness and this is accuracy. See that they are very correlated to each other. And then the others, it's just scattered, it's random. As you can see, toxicity for some scenarios, there's natural questions, but as you can see here, for these scenarios, most of them for robustness and fairness. As you plot them against accuracy, they are correlated. So these are the models we used, including some, and I talked about this in my previous video, how the model creators, the modality, the parameters, the tokenizer, and if you didn't watch it, it gives you a good summarization of what models we have. And there are names like Da Vinci from OpenAI, we have GLM from Tsinghua University, we have T5 and UL2 from Google. Yeah, and these are the models they benchmarked in the research paper. So the model comparisons, we realized that Text Da Vinci 002 was the most accurate. This right here was the most accurate. And then TNLG version 2 is the second most accurate, followed by Anthropic. Models with over 50 billion parameters generally have higher accuracy win rates. Then accuracy correlates strongly with robustness and fairness, which we've already talked about it. Bloom performs better in robustness and fairness than its accuracy suggests. And then rankings for toxicity and bias differ significantly, with some models like TO++ being highly toxic but less biased, while Da Vinci is less toxic but very biased. Then, yeah, as you can see here, this is the graph with the models as we're plotting them against a particular metric. This is, as you can see, this is robustness, uh, this is fairness, this is bias, and still we will see that robustness, fairness, and accuracy are very correlated. The best, the model with the best accuracy is the model with the best robustness and model with the best fairness. Same thing as you go on down below. There are some few variations, but the correlation you can see it properly. Then accuracy as a function of other variables. So accuracy as a function of other variables, these are particular scenarios. So we will notice that there is a relationship between access of like how accessible the model is, that, yeah, as we see here, that AMLU, if the model is accessible, it will actually be its accuracy will be good. But a limited one will have better accuracy. And as we can see, most of these models, we see that the ones which have limited access are most times the one with the best accuracy, because they get this accuracy from the fact that the best shaded bars indicate the performance of the best model for the scenario, whereas the solid bars indicate the performance of the overall most accurate model across all core scenarios. Yeah, so these models, you will notice that the ones which are limited will be more accurate than the ones which are open and closed. What they mean by open, these are open to for research purposes. When the limited are the ones which are sometimes which are both open and closed. Then closed models are models which we actually got for this particular research process, but then they are not accessible to the public, but they were only provided because we were actually carrying out benchmarking of particular models. Then we move on to the prompting analysis. What we refer by prompting, this is a method of guiding language models to produce desired outputs by providing them with the constructed input examples and instructions. And we have featured prompting, providing a few examples of the input and output within the prompt to help the model understand the task. You give it examples of questions and their corresponding answers. Before asking the model to answer a new question, you give it probably what is the capital city of France, then you give it the answer. And then by the time you ask another question, it knows how to answer the question with a particular prompt. So there is also prompt formatting. We have to provide it with the instruction, input prefixes, the output prefixes, and the input suffixes, whereby the instructions are just the instructions, and then the input prefixes is the question, the output prefixes is the answer. So we move on to there is an optimal prompt formatting which varies significantly between models, whereby some particular models, one prompt format might give a particular accuracy, whereas in another model, it gives a very low accuracy. So you see it in, for example, Anthropic Helm is a 67.3% accuracy on natural questions, whereby natural question is our particular data set we use. But then the same format caused Bloom's accuracy to drop from 60 to 8.5%. Then there's also a problem of difference in tokenizers. As we see here, these particular models have different tokenizers, and this also creates an issue with prompting. Okay, not an issue, but the prompting is different. The prompt analysis gives different results. So as you can see here, the multiple choice joint and multiple choice separated, whereby and the multiple choice separate calibrated. So what they mean by multiple choice joint is the particular object or the objectives we know usually, whereby we give we prompt a model while giving it all answers, and we ask for the particular answer. Then multiple choice separate, we give a model a question, and we give those different objectives. We give it to the model, and this model is supposed to provide us with percentages of how accurate it may, how that particular answer may be accurate. And then the multiple choice separate calibrated is the mixture of both. And yeah, so this is how most of these fared, whereby they took a sample of 6 models, and they were sampling them with prompts using different datasets, Killer Swag, OpenBook QA, and they would see. So for example, you see for Bloom here, for multiple choice joint, it shows that with Hella Swag, it's kind of low, but then with multiple choice separate, whereby it gives out the percentage, it's better, it gives out a better accuracy. And then for a mixture, it's just in between there. We move on to open book, whereby it gives a very low for multiple choice, and then it gives for multiple choice separate, it gives moderate, and then for multiple choice separate calibrated gives the best accuracy. So this I was just sampling for Bloom, but as you can see, there are other different models they used, which are 6. And then yes, we move on to the task specific results for core scenarios. We have around 6 tasks, which are question answering, information retrieval, summarization, sentiment analysis, and toxicity detection, and as well as disinformation. But disinformation is going to be talked about in the human evaluations. So question answering, we see that significant variability across the 9 scenarios. Text Da Vinci consistently outperforms others with the highest accuracy on all scenarios of question answering. Many models show poor calibration with notable errors in scenarios like Hella Swag, whereby Hella Swag is our dataset, but consider a scenario here. So models generally experience 5 to 10 point drops in accuracy under perturbations. Then with question answering, low toxicity rates, except for narrative QA, which shows slightly higher rates, possibly due to its domain. Then information retrieval, top models like Text Da Vinci 002 and TNLG achieve competitive scores, and models perform better in a boosted setting, which includes all relevant passages. Then minor drops in accuracy for Da Vinci 002 in perturbations, showing its robustness reduces. Then, which means the future work should explore cross-lingual retrieval settings, and scalability and efficiency are critical. Current models, due to their big size, are less efficient for real-time applications. Then summarization, their ROG scores, very low ROG scores. Models struggle with generating summaries of appropriate length, a low incidence of toxicity through TNLG, although TNLG version 2 has the highest toxicity rate. Models exhibit similar biases in gender and racial representation across datasets. Then sentiment analysis, high accuracy across models. Top models are well calibrated with notable exceptions like Bloom and Helm. Consistent drops in accuracy under perturbations, showing that their robustness is very low. Consistent contrast sets reveal significant drops for top models under semantics altering perturbations. Then toxicity detection, it's generally low, with few models surpassing 60% accuracy. Text DaVinci 002 is the most accurate with 66.8%. Then there's poor calibration toxicity detection across all models. Then significant drops in accuracy under perturbations, showing that they're not so robust, with the most accurate models experiencing substantial decreases. Specific subsets like LGBTQ comments show lower performance. Then we'll talk about the targeted evaluations. Targeted evaluations are the language modeling, the knowledge acquisition, the reasoning capabilities, memorization and copyright, social bias, and toxicity. So we see that models trained on the PILE dataset show high accuracy on the PILE as well as other datasets. All models perform worse on African American English compared to white English, which needs to be worked upon. So all models, as I said before, all models perform worse on African American English compared to white English. That's a repetition. Sorry about that. And knowledge, so we move on to knowledge acquisition. So text DaVinci 002 consistently outperforms other models in knowledge-intensive question answering scenarios, especially in truthful QA and AMLU. So text DaVinci 002 achieves the highest accuracy, followed by TNLG, Cohere X Large, and DaVinci. Then the reasoning capabilities, Code DaVinci 002 and Text DaVinci 002, we lead in reasoning tasks, especially in synthetic reasoning scenarios. Code DaVinci 002 is particularly strong in natural language reasoning. So models struggle with reflecting difficulties in abstract and logical reasoning. Whereas for memorization and copyright, models rarely repeat content, but when they do, it actually includes large text spans. Code models reproduce source code more than non-code models because code doesn't change. So they often reproduce the same kind of code that is in the dataset. Then some models can reproduce significant portions of popular books like Harry Potter. Social bias, text DaVinci 002 shows high accuracy and also has high bias in ambiguous contexts, aligning with societal biases. All models show biases counter to broader societal biases with less correlation between accuracy and bias in these settings. As we saw before, accuracy and bias are not so strongly correlated. Toxicity. Models generate toxic content more frequently when prompted with toxic content. As you give it a toxic prompt, it will provide you with a toxic response. Whereas for non-toxic context, the rate of toxic generation is significantly lower. So as these models, most of them, when you give it a normal text without any toxic language, most of the times it's going to give you text back, which is very non-toxic. So models like YLM generate toxic content in over 15% of cases for toxic prompts, but drop significantly for non-toxic prompts. So as we can see here, the target evaluations of reasoning. As you can see, this is the model accuracy of 12 scenarios, 5 question answering for evaluating reason capabilities. So you see, this is a math data set, this is a math data set. And as you can see, in DIC, it's showing a lot of reasoning. Then entity matching, whereby we are matching, or we are matching particular entities to others, we see that it's actually having a good number of reasoning. Then data imputation, whereby you give it data and it reduces it. We're seeing widespread, but kind of widespread, but still a good amount of reasoning. In legal support, since the data is it's very specific, there's no big spread, and the reasoning is still good, but we are noticing very low reasoning in math and GSMK. This is our whole math data set. And for synthetic reasoning, whereby we are giving it we are giving it questions whereby it has to reason from particular amount of words. It's still, the reasoning is good, but not so good as compared to entity matching. So for copyright, we see that for LSS, we have its model performance was for copyright is really low, but we have some outliers whereby it actually happened. Then for code, like we talked about it before, code, there is very many instances whereby code is going to come out and the code is similar to what we've had before. And after a few editing of the simulation, we will see that the copyright is actually reduced to almost zero. So we move on to the human evaluations. So this evaluation shows that language models are good at creating convincing arguments and realistic sounding text in various styles. However, it's hard for these models to create messages targeting certain groups. It so happens, but it's very rare. Like there is an example of text Da Vinci created by GPT. It has been seen to associate Muslims with violence, but then it's not. Most of them don't do that. The people who reviewed the text were people who actually review these the texts are regular crowd workers, not experts in identifying this information. This might mean they rated the text more favorable than experts would. Additionally, the evaluation did not include models that might be purposely made by bad actors to spread disinformation. So the real threat of such models could be higher than what was found in this study. So in conclusion, the study suggests that while these models are pretty good at making believable and varied text, they still struggle with tailoring messages to specific audiences. The true risk of these models in spreading false information could be worse than what the study shows, especially if bad actors create special models for this information. Yeah, hello. I'm back to take you through the related work and discussion. So as you've already seen, language modeling has been a significant area of study for decades. It has been being carried out for decades and decades, evolving from simple generative models to complex foundation models. The success value models like GPT and BART led to a rapid increase in the size and complexity of language models, with some now being way larger than their predecessors. These advancements required significant computational resources and led to the integration of language models into commercial products and APIs. As we can see, most uh, most most people are adapting to ChatGPT, Gemini. There are very many uh, language modeling language models that are being used right now. So benchmarking has long been a critical method for evaluating natural language processing models, beginning with initiatives like the message understanding conference and the text receive or retrieval conference way back in the 1980s and 1990s. So the discussed work introduces a holistic approach to benchmarking of language models. So unlike traditional benchmarks that provide a single score of a vector, this approach of holistic uh, evaluation of language models uses a score matrix to evaluate models across multiple metrics like accuracy, robustness, fairness, bias, toxicity for various use cases. So there is no common standard for evaluating these language models, especially given their evolving capabilities and potential harm. So what is missing in this research paper? So the current benchmarks focus on classical user-facing tasks. Other significant tasks as syntactic, parsing, and natural language inference are missing. Emerging tasks from new applications like copywriting and creative generation need evaluation methods. Important domains like biomedical, financial, education, and customer service data are not covered. The focus has been mainly on English, but there is a need for broader language coverage, especially for diverse languages and culturally sensitive evaluations. Missing metrics include user experience, linguistic plausibility, and credibility. So there are also some missing targeted evaluations, including planning and various forms of model harms like spam generation, fraud, dehumanization, and condensation. Most models are accessible but not evaluated. Models like Galactica, some are disclosed but inaccessible. Models like DeepMind, Google, uh, should be benchmarked, and new mechanisms for model access should be considered. Exploring various adaptation methods, e.g. prompting strategies, parameter efficient methods for fine-tuning and their interoperability across scenarios, metrics, and models is essential. The limitations on the future work. So we have limitations of results. The findings may not be universally applicable to all particular practical scenarios. So results may not be fully generalizable due to potential contamination of the test data they used without training sets, given the vast and undocumented data sources used in training these models. The results are influenced by the chosen method of adaptation, e.g. prompting. We used prompting. Limitations of benchmark implementation. The benchmark lacks comprehensive coverage of missing elements, although it can be generalized to evaluate any foundation model. There is no unified standard for ensuring dataset validity and reliability. Future work should focus on verifying the validity of datasets and establishing protocols to ensure it. So the limitations of the benchmark design, unlike simpler benchmarks that provide a single score, the holistic approach results in complex score matrix. The detailed results can overwhelm users by not understanding them. So the document also acknowledges the usefulness of single number metrics for decision making, but leaves the challenge of aggregating complex performance data into single metrics for future work. In conclusion, language models have become very important in AI and are now used in many real-world applications. We don't fully understand how they work or their impact, which is a problem as they become more common. To fix this, we need comprehensive evaluations to make these models more transparent. This will help build trust and set standards. Benchmarks which guide AI development should be inclusive and democratic. The authors of this particular research paper want the community to improve Helm to ensure that these models are useful, responsible, and beneficial to the society. And this brings me to the end of my video, and thank you for watching.